Okay, so I believe we are online. So let us start with the lecture. So welcome to the 10th lecture of this course on solid mechanics. And today is the last lecture on stresses. So since lecture 2, we are talking about traction and we are talking about stress. We talked about transformation of stress. We talked about principal stress, principal plane, maximum shear stress. So all of this we talked about. We also talked about Mohr circle. And that is what we will be continuing with today. So we will be talking about Mohr circle, some new concept as well as some old concepts. So that is what we will be doing today. And today is the last lecture, as I was saying, on stresses. And from the next lecture, we will start discussing on strains, and we will revisit all the things on stresses that we talked about in strains as well. Now, the discussion on stress has mostly been or has completely been on uh, Cartesian coordinate system. Obviously, the same concept is also applicable to the cylindrical coordinate system, but that is not what I have discussed. Similarly, you will see that when I will be talking about strains, I will be talking about strains from a Cartesian coordinate system. And again, the concepts will be equally applicable to the cylindrical coordinate system. So once I'm done with strains, I will revisit stress and strains, both of these concepts, but from a Cartesian coordinate system. And we will see that the concepts are more or less similar. So without any delay, let me share the screen now, and then we will talk about Mohr circle and some other important topics on stress. So let me share the screen. So I think my screen is visible now, and let me switch on the pane mode, and now we are ready. So what have we discussed till now on Mohr circle? To start with, we discussed that Mohr circle is a graphical way to compute stress components. And when I say stress components, I mean that normal component of stress and shear component of stress. So Mohr circle is a graphical way of computing normal component and shear component of stresses on an arbitrary plane. That is what Mohr circle is. And then we also discussed that Mohr circle is only applicable if one of the coordinate axes is along the principal direction. So for example, if you remember, we talked about this coordinate system previously. So X, Y, and Z. So this was our coordinate system, and we considered that this Z direction. So this we considered it to be our principal direction. So at least one of these three has to be the principal direction. So this is also something we talked about, right? That at least one of the three direction at least one of the three direction. And what are the direction? X, Y, and Z. So at least one of these X, Y, and Z direction should be a principal direction. So this is something we talked about, right? And with this assumption, what was the state of stress looking like? So we considered Z to be the principal direction. And with this assumption, our stress matrix looks like looks like something like this, right? Sigma xx, tau xy, tau xy, sigma yy, 0, 0, 0, 0, and sigma zz, which is equal to sigma 3, the third principal stress, right? So this is how the stress matrix will look, uh, uh, or this is how the stress matrix should look, so that we can use Mohr circle. However, this condition is not sufficient. This is an essential condition, but this condition is not sufficient. There is one additional condition, and that condition is, so Mohr circle can be used to compute stress components Mohr circle can be used to compute stress component on plane alpha, where alpha is equal to alpha 1, alpha 2, alpha 3, if and only if alpha 3 is equal to 0, which means that if there is an arbitrary plane for which I want to compute the normal and the shear component of stress, that arbitrary plane will have to be perpendicular uh, to this z-axis. So basically, we are rotating about this z-axis. That is what this condition is telling us. And why alpha 3 is equal to 3? Because we considered z to be our principal direction. In case you consider x to be the principal direction, then you will need alpha 1 to be equal to 0. And if you consider y to be the principal direction, you will need alpha 2 to be equal to 0. So these are the conditions under which you can actually use Mohr circle, and these are the conditions that we already discussed. Now we also arrived at the relation that sigma n, that is, and what is the sigma n? Sigma n is normal stress component on an arbitrary plane n. That is what sigma n is, and we found out in our on Friday's lecture that sigma n is equal to sigma average. So this term you are seeing, sigma xx plus sigma yy by 2. This is also we denoted it as sigma average. So sigma n is sigma average plus r cos 2 phi minus alpha. Now what is this r? So you remember so for defining r, we considered a right angle triangle such as this, where our the height of the triangle was tau xy and the base was sigma xx minus sigma yy by 2, and this angle was 2 phi, and the hypotenuse was r. So basically r, to remember, is defined as sigma xx minus sigma yy by 2 square plus tau xy square. So this is how we define r. And then there is this phi. So tan of 2 phi is defined as tau xy by sigma xx minus sigma yy by 2 which implies that phi is equal to half tan inverse tau xy by, we can write it 2 tau xy by sigma xx minus sigma yy. So this is what you can use to find out phi. And remember that this phi is the angle between, so this phi, let me write it down also, that phi is the angle between the E1 plane and the first principal plane, right? So phi is the angle between the E1 plane and the first principal plane. So if you draw the triangle, not triangle, if you draw the circle, so this is your center, which is sigma average comma 1, and then this is your sigma xy, and then we drew a triangle such as this. So this is your 2 phi angle, and if you rotate this 2 phi, so if your 2 alpha is equal to 2 phi, so if you rotate it by 2 phi, 2 alpha is not, so yes, so if you rotate it by 2 phi angle, what do you get? This point, and this is your first principal plane, EP1, let us say. And so this is your 2 phi, so phi is the angle between the E1 plane and the first principal plane. And the second principal plane is basically phi plus 90 degree. So if you see here, this is E1, this is E2. So this angle is 180 degree. And in the real, I mean, in the Mohr circle, if it is 180 degree, in reality, it is 90 degree. So it is phi plus 90 degree. That is what the angle is. So we also saw that cos 2 phi is sigma xx. So basically, again from that triangle, you get both these results as you see here, and then this is r. So these are the things that we have discussed. We have discussed in yesterday's lecture, right? Not yesterday's, I mean Friday's lecture. So now let us try to solve one problem using Mohr. So I will only show you how to draw the Mohr circle. The exact values you can find it on your own. Okay. So this is my state of stress. So the state of stress is given in this form. This is my state of stress. Okay. Now, the first question is, so what is question 1? The first question is, can we use Mohr circle for this sigma? Can we use Mohr circle for this sigma? That is the first question. And the answer to this question is yes. Yes, we can use Mohr circle for this state of stress, because clearly sigma, this E3 plane or the Z plane is a principal plane. So our minimum condition is satisfied. E3 or Z plane is a principal plane. So we can actually use Mohr circle and find out the principal stresses. If I ask you, can we use, so let me ask the question 2. Can we use Mohr circle for this sigma to compute sigma n and tau n on the in plane. So can we use it? The answer to this question is yes, if n3 is equal to 0. Otherwise, no. So yes, you can use it if n3 is equal to 0. Otherwise, no, you cannot use it. So these are the two basic questions. So for now, we are interested in computing the principal stresses, sigma 1 and sigma 2. So the answer is yes. For this state of stress, we can compute the what should I say? We can compute the principal stresses, right? So now let us see how we can actually compute the principal stresses. So let me clear it up, and then let me draw the Mohr circle. So the first step is, so I will write the steps here and also draw the circle. So steps. So what is the first step? Draw the sigma n and tau n axis. So I am going to draw the sigma n and tau n axis. So this is my sigma n axis, and this is my tau n axis. So let me write sigma n here and tau n here. So that is step 1 is done. Step 2 is identify sigma xx and tau xy on the sigma n tau n plane. So this is now my second step. So what is sigma n and what is sigma n and tau n plane is this one, whatever you were seeing. So what is my sigma xx? Sigma xx is 1 by root 2. So let us say this is my sigma xx, okay? Let us say this is my sigma xx. So let me change the color. The color I will take blue. So this point is your sigma xx, and then if you go in the vertical direction, let us say this point you see here is 1 by root 2, comma 1 by root 2. Okay. Now the second step will be to find out the center, and the center is, so not the second step, the third step, right? So third step is compute sigma average, and sigma average is sigma xx plus sigma yy by 2, which is also 1 by root 2. So this point you see here, this is actually your center. So this is my center, which is sigma average, comma 0. So I have my center, I have this point, so I can connect these 2 points, right? And this is my radius. And now I am in a position where I can draw the circle. So let us draw the circle. Let me change color once again. And now let us draw this circle. Okay. So yeah, so let us say this is my Mohr circle, right? So this is R, as you can see. This is sigma average comma 0. So now what is the value of sigma average comma 0? So this value is 1 by root 2, right? And what is the value of R? So the value of R is actually, you will find the value of R is, I mean, you can actually measure it in Mohr circle. You are not going to compute it, so you are going to measure it, but we know the formula. So using the formula, it is sigma xx minus sigma yy by 2 square plus tau xy square. Now this term is 0 in our case because these two are equal, which means R is equal to tau xy. So this is also 1 by root 2, which means this axis is wrong. This axis should have, I mean, this should have been my tau axis. So, I mean, okay, I did not know the result beforehand, and this circle is not scaled, but yeah, in this case, this passes through the axis actually. So this is actually your tau n axis. So this circle will cut the tau axis at 0. Okay. So what is my principal stress now? Obviously, one of the principal stress is going to be 0. Right. The other principal stress is going to be 2 into 1 by root 2. So the other principal stress is going to be root 2. So one is here, the other is here. So this is 0 and this diameter. The radius is 1 by root 2 and the diameter is twice 1 by root 2, which is root 2. So the principal stresses are root 2 comma 0. And obviously the third one is 1. Now let us use the formula that we have shown here. So the principal stress formula is not here. So obviously we cannot use it, but first we have to use this one. So let us see. We want to find out phi, right? And for that, so what is sine phi? Let us see. So sine 2 phi, if we use the formula, is tau xy by r. So what is tau xy? 1 by root 2. What is r? 1 by root 2. So this is 1 by root 2 by 1 by root 2, which is 1, which means 2 phi is equal to 90 degree, which means phi is equal to 45 degree, right? So now phi is equal to 45 degree. Now if you want to compute the principal stress using this formula, you are going to replace alpha with phi. So this term becomes cos 0. This term is going to become cos 0. So this will become 1. Cos 0 is equal to 1. So your sigma n is actually sigma xx plus sigma yy by 2 and then plus minus r, because there are two principal stresses. So sigma p1 is plus r, sigma p2 is minus r. So what is sigma xx plus sigma yy by 2? 1 by root 2 plus 1 by root 2 by 2. So 2 by root 2 by 2. So this is 1 by root 2. And then plus minus, what is r? 1 by root 2. So what is the final result? 1 will be equal to 2 by root 2, which is root 2, and the other will be equal to 0. You see, you are getting the same result that we got from the Mohr circle. Now there is another concept in Mohr circle which is known as Mohr's stress plane. And this idea, for explaining the idea of this Mohr's stress plane, we are going to consider the three principal stresses. So we are working, or we are at this moment at least, we are working with a coordinate system such as this, where this is my E1 plane, and E1 plane is actually the first principal plane. First principal plane. This is the E2 plane, which is the second principal plane. And similarly, this is the E3 plane, which is the third principal plane. Right? So we have three planes here. One is the first principal plane. So all the three axes are the principal planes. So we are working with the principal coordinate axis, right? So with this, what we are going to do is, so this is my sigma n plane, and this is my tau n plane. Okay. So first, what we do is we determine, or we point out the three principal stresses. So we are going by this notation: sigma 1 greater than sigma 2 greater than sigma 3. So accordingly, this is my sigma 1, this is my sigma 2, and this is my sigma 3. So now, wait. So case 1, consider consider sigma 1 and sigma 2. So basically, consider the plane that is perpendicular to sigma 3. So consider sigma 1, sigma 2 plane, which means the plane, this plane is perpendicular. This is perpendicular to sigma 3. So if we consider sigma 1, sigma 2, how will the Mohr circle look? Well, the Mohr circle should pass through this sigma 1 and this sigma 2. So this is how your Mohr circle will look when you are considering sigma 1, sigma 2. That is, your plane is perpendicular to sigma 3. Next, let us consider sigma 2 and sigma 3. So in that case, our Mohr circle will pass through sigma 2 and sigma 3. So this is what we will get. And lastly, we consider sigma 1 and sigma 3, which means the Mohr circle will pass through sigma 1 and sigma 3, which means this is going to be my largest Mohr circle. And let us say this is the Mohr circle. Now compute sigma n for arbitrary n's. So compute sigma n and tau n. So compute this state of stress matrix for arbitrary n's, and then you plot it on this sigma n tau n plane. So let me repeat myself. Compute sigma n and tau n for arbitrary values of n's, and then you can plot it on this sigma n and tau n plane. And if you do that, you will find that all these sigma n's will lie here. All the sigma n's will be here. So these are all sigma n's. The dots that I am drawing are all sigma n's. So what can you see from here, whatever I am drawing? You can see that the sigma n's are actually lying in a special area, which is, what can we say? We can say that sigma n resides inside the largest Mohr circle, but no sigma n exists within the two smaller Mohr circle. So you see all the sigma n's will reside inside the largest Mohr circle, but you will not find any sigma n inside the two smaller Mohr circle. So this plane where the sigmas lie is known as Morse stress plane. So the portion I have marked with dots using the magenta color, that is known as the Morse stress plane, right? Now, what can you say about this Morse stress plane? So in this Morse stress plane, we have this sigma 1, sigma 2, and sigma 3. This sigma 1 is clearly the largest or highest sigma n. So this is basically the maximum sigma n. So this is basically my maxima. This is the maxima. This is the global maxima actually. So throughout this stress plane, you will not find another sigma which is bigger than this sigma 1. And similarly, this sigma 3 you are seeing, this is the minima. And this is not only the minima, this is the global minima, which means throughout this Moore's stress plane, you cannot find another sigma which is smaller than this sigma 3. But then what about this point sigma 2? This is also something we found out by this is also something we found out by taking the derivative of the generalized stress on an n plane and making it equal to 0. You remember the derivation of the principal stress? The principal stresses were derived by making the derivative of the principal stress or of the stress component on an arbitrary plane n to be equal to 0, and that is how we got sigma 1, sigma 2 and sigma 3. And now we are saying that okay, sigma 1 and sigma 3 are respectively the global maxima and global minima. But what about this sigma 3? So if you take this circle, and which is not a circle, a square. So let us take this square, and then you will find that okay, you have a line such as this, and you have a line such as this. So if you take the points within this circle, this stress plane, there are sigmas. So there are sigma n greater than sigma 2, and on the other hand, this side, the sigma n is less than sigma 2. So which means this sigma 2 is neither a global minima and neither a local minima, because sigma 1 is the global minima and sigma 3 is the local minima. So the first conclusion is sigma and sigma 2. So which means sigma 2 is neither a local minima and nor a local maxima. So sigma 2 is not optimal from a global point of view, and sigma 2 is not optimal from a local point of view. So what is sigma 2? Why is at sigma 2 the derivative equal to 0? Sigma 2 is what is known as the saddle point. Sigma 2 is a saddle point. So what exactly is a saddle point? So if you are solving an optimization problem, a saddle point is something like so if you have a horse, so on the back of the horse where you sit or where a person sit, so that is what the shape of a saddle is. So suppose we have this plane. So we have this XY plane. So a saddle point will look something like this. So what can you say from this plane? So on the X plane, so this is the X axis, this point, so in X, this is minima. So let us say A. So A is minima. Whereas if you draw it properly, so it will look something like this. And in Y, so this is the Y direction. A is maxima. And under this condition, you get the derivative to be equal to 0. And this point is known as the saddle point. So sigma 2 is neither a maxima nor a minima. It's a saddle point. Okay. Now we also talked about tau, right? So we also talked about tau. So what about the tau? So the maximum tau is here and the minimum tau is here. Magnitude wise, both of these are maxima. But if you take the sign also, this one is maxima and one is minima. So these are the global optima. Global optima or tau. But then we also have these points. What are these points? Are these global optima? Obviously, these are not global optima. But the question is, are these local optima? The answer is again no. So if you do the same thing, take a small box, you will find tau. So this, let us say this is tau 2, let us say. So you will, and then you will find at this location tau n, and also in this location tau n. So you will find tau n point, same logic for this point, all these tau are also the saddle point. So even this tau are the saddle points. So there is global optima and then there is saddle points. There is no local optima as at least from this Mohr's stress plane. Now let us do something interesting, okay? So let me go back and clear it up. So now let us consider a special case. So let us say that for our case, sigma 2 is equal to sigma 3. So in that case, what will happen? This circle, see this sigma 2 is proceeding towards this sigma 3. So this circle will shrink. This circle will shrink, right? And this side circle will expand. And in the limiting condition, what will happen? This sigma 2 will come here. So in the limiting condition, you will have, so this circle has shrinked, and this circle will coincide with the larger circle. So now this is my sigma 2 comma sigma 3. This point does not exist. And what is now my stress plane? Remember, inside sigma 2, the stresses don't exist. The stresses can exist only inside the bigger circle. But now the bigger circle is coinciding with one of the smaller circle, and in that case, your Mohr stress plane reduces to a Mohr circle. So in this case, Mohr's stress plane reduces to a Mohr circle. So this is a special condition where you will not find a Mohr stress plane because that will become a Mohr circle. Okay. Now let us take another special condition. And in this case, sigma 1 is equal to sigma 2 is equal to sigma 3. Now this is a case which we have discussed earlier, and this is known as hydrostatic state of stress or isotropic state of stress, right? Now if sigma 1 is equal to sigma 2 is equal to sigma 3, so let us say this is the point. So this sigma 2 is equal to sigma 1 and which is equal to sigma 3, what will happen? All the side circles will reduce to a point. So circles or Mohr circle reduces to a point. And remember, in this case, all directions are principal direction. This is something we discussed earlier, right? So that is Mohr's stress plane. Now there are some other concepts that I would like to discuss. So these are concepts which are related to state of stress, but not really to Mohr circle. And the first such concept is octahedral stress component. So what is octahedral stress? So if we consider a principal direction as the coordinate axis, so that is what is written here, then the plane whose plane normal forms equal angle with the coordinate system is known as the octahedral plane. So what does it mean? So we have this equation, right? L square plus m square plus n square is equal to 1. And now as per this condition, we have L equal to m equal to n, which means L square is equal to m square is equal to n square is equal to 1 by 3, which means L equal to m equal to n is equal to plus minus 1 by root 3. So that is what octahedral state of stress is. But you should be very careful. This L equal to m equal to n equal to plus minus 1 by root 3 is with respect to the principal direction, is with respect to the principal planes. It is not respect to any arbitrary plane. So this is something you should be very careful about. Often people make this mistake, and they try to find out, they think that octahedral stress is always when L equal to m equal to n equal to 1 by root 3. No, this L equal to m equal to n equal to plus minus 1 by root 3 is always with respect to the principal direction. If it is with respect to some other direction, that is not octahedral state of stress by definition. Okay. Now, another question is, how many such planes are there? So you can see that L can take the value plus minus 1 by root 3. m can take the value plus minus 1 by root 3 and n can take the value plus minus 1 by root 3. So total there are 8 such planes. So 8 and octa. So you can understand the relation, right? Octa means 8. So there are 8 such planes. And that is why the name octahedral. Okay. Now, what are the normal component of stress and shear component of stress on this octahedral state of stress? So let us try to find out the normal component of stress and the shear component of stress on this octahedral plane. Okay. So remember the relation. If you want to, what is sigma n? Sigma n is sigma 1 1 or sigma 1 because we are considering the principal plane L square plus sigma 2 n square plus sigma 3 n square. Now in the octahedral plane L equal to m equal to n or L square equal to m square is equal to n square is equal to 1 by 3, which means it is equal to sigma 1 plus sigma 2 plus sigma 3 by 3, which means it is equal to I1 by 3. You remember I1, the first stress invariant, which was defined as the trace of the stress matrix. So this is your octahedral stress. Okay. Now next, what about the shear one, right? So what is the shear stress? Let us see. Shear stress square is magnitude of the traction vector square minus sigma n square. So what is the magnitude of this traction vector square? It is sigma 1 square L square plus sigma 2 square m square plus sigma 3 square n square minus this is I1 square by 9. So this is from this expression, right? Now this is sigma 1 square L square plus sigma 2 square N square plus sigma 3 square N square, right? So now if I put the value of this L, this is basically sigma 1 square by 3 plus sigma 2 square by 3 plus sigma 3 square by 3 minus I1 square by 9. Now what I want to do is I want to compute I2 for the principal stress matrix. So what is I2? I2 for this, I2 for this one. So I2 for this one is sigma 1 0 0 sigma 2 plus sigma 2 0 0 sigma 3 plus this one is sigma 3 0 0 sigma 1, which is equal to sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. So this is your I2. Okay. Now what is the formula of A plus B plus C whole square? A plus B plus C whole square is equal to A square plus B square plus C square plus 2AB plus 2BC plus 2CA, which means A square plus b square plus c square. I can write it as a plus b plus c whole square minus 2ab plus bc plus ca. Now, in the context of this sigma, if you look into it, what is this a plus b plus c? This is I1, right? So we have I1 square minus 2, this is I2, which means, let me clear up some space, which means, actually I don't want to clear up this space. So we have this one, right? So let us see what we can write. So this is sigma 1 square plus sigma 2 square plus sigma 3 square. So, okay, actually I can clear up the space above that, right? The bottom one I need, but this one I can remove. I mean, I1 by 3 is already established. So, let us see. You can already understand that what I'm getting at. I'm going to represent everything by I1, I2. Okay, so that is what the goal is actually. So let us see. So this one I'm writing. Okay, so I have 1 by 3 outside. And then inside I have sigma 1 square plus sigma 2 square plus sigma 3 square, which is sigma 1 plus sigma 2 plus sigma 3 whole square minus 2 sigma 1, sigma 2, sigma 2, sigma 3 plus sigma 3, sigma 1, right? And then what do I have? Minus I1 square by 9. And remember, this is tau n square, not tau n. So now when I write it, 1 by 3 is there. Inside the bracket, what do I have? This is I1 square. Minus 2, this one is I2. So minus 2I2 minus I1 square by 9. So what do we have? I1 square by 3 minus I1 square by 9 minus 2I2. So basically if you combine these two, you have 9. So this is 3 minus 2. So 2 by 9 I1 square minus 2 I2. So let me write it here. So tau n is equal to square root of 2 by 3 I1 square square root of 2 by 3 I1 square minus square root of 2 I2. Right? Yes. So this is the form that you get. This is the same form that we just showed you. So if you take the square root, you will find that this will become square root of 2 by 3 I1 square minus square root of 6 is square root of 6 by 3. So if you take 3 inside, it will become square root of 6 by 9 actually. I2. And then when you cancel it out, it becomes 1 by 3. So square root of 2 I1 square by 3 minus 1 by root, this becomes 2 by 3 actually. So square root of 2 by 3, so square root of 2 can come outside. Okay, so let me erase this part so that there is. So now this is square root of 2 by 3. Square root of 2 is outside, so this is I2 by square root of 3. So this is your octahedral shear stress and octahedral principal stress, octahedral normal stress. Now what can you tell from here? see I1, I2, both of these are invariant, which means both these stress components are also invariants. So sigma oct and tau oct are also invariants, right? So that was one important concept. And then there is the last concept, which is hydrostatic state of stress. We've already discussed it, and the volumetric state of stress. So any state of stress can be divided actually into hydrostatic and deviatoric state of stress. So what is hydrostatic state of stress? So hydrostatic stress, also known as the volumetric stress, is a component of stress which contain uniaxial stresses but not shear stresses. So basically sigma height, this is hydrostatic state of stress. You see all the principal directions are, all the normal directions are equal. So this is a classical example of where sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to sigma h. And when do we come across such a state of stress? Well, if a body is inside a fluid, that body experiences hydrostatic state of stress. And under such circumstances, this is what you will get. Now, hydrostatic state of stress is also responsible for the volume change or volumetric strain, which we will talk later. And that is why this is also known as the volumetric stress. Okay. And then there is deviatoric stress, which is if you have an arbitrary state of stress, let us say sigma, and if you subtract sigma HYD from that, whatever you are getting is a deviatoric state of stress. Now, this deviatoric stress will not result in change in volume, but it will change in the deviation of the shape. So if a body was something like this, that body can become something like this. And this distortion is due to deviatoric state of stress. But if there is only deviatoric state of stress acting on a body, the volume will not change. So if this is V1, this is V2, V1 will have to be equal to V2. When the body is under the action of a deviatoric state of stress. Okay. Then obviously, since this is how we define it, any state of stress can be expressed as a deviatoric state of stress. So in any case, we will stop here for today. This was the last thing of stress. There are some other things which you may come across while solving the assignment and not the homework. So assignment will be given to you very soon, the first assignment, which will be on all the things on stresses that we have covered. And there you may come across some new topic, but otherwise we have covered all the things of stresses. And from next lecture, we will be talking about strains. So we will talk about strain in a body from next lecture onwards. So thank you, and we will meet again in our next lecture.